I guess we can get started by, I guess I'll just make everyone aware of the one due date that's upcoming, and that is for the quiz, which is pretty much on normality. And this quiz is due tonight, so please make sure you do that by tonight. Additionally, I went ahead and posted a practice test for exam 2. This is what we're going to be covering in class today. Just like with exam 1, this practice test will have no bearing on your grade. You can do it, you don't have to do it, it doesn't matter. It's there for your reference. It pretty much gives the ceiling of problems to expect. Of course, not all 32 problems on here are going to be on the test, but if you can do this test and you get 100% on it and you feel comfortable with the material on it, you should do fine on the test. And then, of course, the test is Wednesday. So just like the previous test, Wednesday's test is in the in the library. So we're taking it in there yet again. So I'll send an email to remind everybody. But again, the second test, of course, is Wednesday during class time in the library. So quiz tonight, practice test we'll go over now, and you can do it on your own if you want, or you don't have to. And then test 2 is in the library on Wednesday. So I think that's pretty much it. Does anyone have any questions for me before we get started?
Will we be able to bring a flashcard? Like
yes, good question. Yeah, so you could bring the flash card again. So you get the flash card. You can put, again, whatever you want on it. What size of the flash card? Again, I'm not going to check it. I didn't check it last time. I trust your judgment. Besides for that, of course, same materials, bring a writing utensil, your calculator, of course. Also, I forgot to ask this last time, bring your Southeastern ID, please. Please bring your Southeastern ID. So again, I'll remind everybody to bring it, but so if you don't know where your Southeastern ID is at, maybe a good time to go find it, or a driver's license would be perfectly sufficient, either or. Besides for that, is there anything else before I get started? If not, then what we're going to do today, as I mentioned, just open up the practice test, go through problems until we run out of time, pretty much. Okay, so again, not every problem is going to be on the test. This is a ceiling of problems to expect. It gives a wide diversity of material on here. And so we could start off with, let's go ahead and start off with this problem. So every 18-ounce bag of cookies for some snack company, something about 1,000 chocolate chips. And the first thing I notice in part A, and the problems are shuffled here so we can kind of see what the problems are like in no particular order for the time being. We want to make them unshuffled later on. But ultimately, they give us a list of data, and they mention something about normal distribution. So we're thinking about chapter 7 stuff. So stuff we did in chapter 7 on normal distributions. So a normal probability plot. And so notice how it's saying observed values and expected z-scores. Now, what these could correspond to, normal probability plots was something we talked about right at the end. And in fact, if you need a reference, in the notes, this was in the last section we went over. We did normal probability plots in the calculator. So it'd be a fairly similar process. So we're just going to go ahead and do that for this data set and remind ourselves about how this process works. Now, there's, of course, on the test, I'm not going to ask for nearly all of these. I'm not typing all these in the calculator. But I just want to demonstrate the process of how we would do this with a much smaller data set.
And it doesn't matter the order that you put the numbers in. Right?
It does not matter the order. You can put them in any order. It looks like these happen to be organized already, so that's just convenient for us if we needed that to be, but it doesn't matter. So again, I'm not expecting you all to type, this is a lot of numbers here. This would be if we were using StatCrunch or something, or Excel. So you would type in all of your numbers. I'll type in the first column just to give an idea of what you would do for this process. You get on the test, maybe I'll put like 10 or something, it wouldn't be that many. 1, 1, 4. So you would type all of these in, and as the notes specify, after we type in the values, you would press second and y equals. Second and y equals is up here, right above second. Yours might already be active from the last time. If not, make sure on is selected. So now on is highlighted, and make sure whatever the last graph is, some calculators might be a little bit different. Make sure the very last graph is active such that you have data list and data axis that appear. Okay, so second y equals. We have now resembled the screen below. Press zoom and zoom stat. So zoom. Yours might have a few more options, but zoom stat. So after you click zoom right here, zoom stat, and it will give you the graph. So this is just a reminder. And also to figure out the particular points, we did this in class before. You want to know what these particular points are, you would press right next to zoom, there's trace. Click on trace, and you can move your cursor left and right to figure out X value is and the corresponding Y value. Now what the Y value represents, as a reminder, and it says it in the notes, the expected Z-scores. So it's the expected Z-scores. And so, of course, I didn't type in all the data values, but you would choose whichever graph or construct whatever graph, whatever the situation may be. It would most likely correspond to the notes as much as possible in terms of on-paper application. And then, so that was just a demonstration. Again, you would pick whichever graph that the scatter plot most closely resembles. After that, you find the mean and the standard deviation, which is pretty straightforward. Once you clear out of this, of course,
we're going to have to draw the scatter plots, or will there already be like one that we choose from on the test?
Well, as far as the scatter plot, you might have to draw one, but the if you were expected to draw one, I would give you a template, and in the X and the Y's, well, I mean, the graph's already given to you here. You basically have to just take whatever your calculator says and write it to the graph, and you might think, well, you know, you can put the shape correctly, but do you put it, how do you put it in the right place? Well, that's where trace helps you. Notice how it gives you an X and a Y. And so you can build the scatter plot pretty easily. And again, I'd give you 10 points, not 50 like this problem does. So you could use this and construct your scatter plot accordingly by using some graph template I give you. You're basically just putting dots down in somewhat you know, reasonable places to resemble this shape. But that any graphing on here that you see will pretty much be expected that you do know how to write it down on paper. but I will give a template, at least for the grid. I believe, so notice we've done this before. So it'd be similar to example 1 in the 7.3 section. Okay. Additionally, so the mean and the standard deviation, you would find that as if you'd find the mean and standard deviation of any general data set. You already have the data set in the calculator, and all you'd have to do is just go one variable statistics to find the mean and the standard deviation. Now it does say standard deviation of the sample data, so we would use the sample standard deviation. Again, these values aren't going to be right for this problem because I only put down the first column. But mean and sample standard deviation, pretty straightforward stuff. Might be expected to translate the information to a normal curve. Remember, any normal curve is always centered around the mean. So whatever the mean that we get is, you would have to make sure that the middle of the graph corresponds to that mean. So this would say that the mean is a little bit over 1,000. This one says the mean is about 1,400. This one says the mean is 1,200. This one says the mean is roughly 1,200. And then remember, the displacement from the mean is the standard deviation. And then since we're dealing with normal models, so this is kind of a two-part problem in a sense. This deals with not only normal probability plots, this also deals with normal probabilities as well. And this is that whole idea that we talked about in section 7.2, where at least 1,000 chips refers to when X is greater than or equal to 1,000. It was this whole idea of having to rewrite it to a way that we can either use the table in the back or binomial probability or cumulative distribution functions. Now this one says normal distribution, so we use the table in the back. Now again, on the test, I will provide 3 graphs that are in the notes. I'm providing this this right here, this other z-score chart right here for the standard normal, and I'm providing this table as well. So anytime we deal with normal distributions and probabilities pertaining to them, we're using this table. Now, this is that whole process where we have to figure out, well, 1,000 or X is greater than or equal to 1,000 is not going to be helpful. We have to do 2 things to make normal distributions actually, readable using the table. Convert to a z-score, make sure the area represents to the left. So instead of X is greater than or equal to 1,000, one thing we have to do is convert this to a z-score. So how do we figure out the z-score? Well, we need to know the mean and the standard deviation, which if you were to have worked out this problem, the mean and the standard deviation would be the values you find here and here. For demonstration purposes, I'll just do it for the values I typed in. So remember, to convert to a z-score, it's the value minus the mean divided by the standard deviation. And that's a very important formula to know. And notice how I'm using Z now because we've converted to a Z-score. And this is a pretty quick computation here. 121.25 to negative by 20.82. I see the problem with approximating in this manner is I found a not realistic Z-score. It's one of the inherent problems with using a very specific subset of values. Now, this Z-score is not going to show up on the table because, again, this is an unrealistic Z-score because I drastically simplified the problem. I could probably figure out the mean and the standard deviation pretty quickly. By using this. I haven't dealt with this too much. Stats, calculators. Expression, no. Well, it'll probably just take too much time for me to figure out how StatCrunch works, to figure out the mean. I know there's some way to do it. I haven't messed around with this too much. Oh, wait a minute. There we go. Okay. Never mind. There it is. Okay. So it seems like the mean and the standard deviation are given here and here. So if you were to have typed all those values out in the calculator, you would have found those two. So let's go ahead and write those down somewhere. Mean is 1246.775. Standard deviation is 100.49. One, 246.775, 100.4. Okay. 6.775. And that's much better, much better. Then we get a true Z-score, negative 2.46, which is reasonable. Normally, Z-scores fall in between negative 3 to 3. Well, standard deviations from the mean, ultimately. We normally get a Z-score that's at the least negative 3 or at the most 3. It's pretty abnormal to get things outside of that. And the reason why I was so adamant about us getting an actual Z-score that we can use is so I can demonstrate how this works in the table. Now, the Z-score is negative 2.46. 2.46 is the Z-score. We have two tables for the Z-score. The first table is the negative Z-scores, so that's the one I'm going to utilize because we have a negative Z-score. So negative 2.46, negative 2.4 puts us here. 6 is right here. And so the area we get 0.0069. Point zero, 0.0069. But there's a problem here. We can't use 0.0069 as the answer. Not yet. There's a greater than or equal to sign. That table only works whenever we have a less than or equal to sign. So we have to complement this. So it's really 1 minus P of Z less than negative 2.46. So really we're looking at 1 minus 0.0069. That will give us the true answer. Because notice this complement, by applying 1 minus, now we can flip the inequality. That means we're looking at the complete opposite part of the graph. Oops. And so this difference, 1 minus 0.0069, 0.9931, is the probability. And it does say it's kind of tricky around 3 decimal places. Again, on the test, if I say round to a certain number of decimal places and you put an extra decimal, you leave off a decimal, not a big deal. I'll probably just give you your full points, unless you're cutting off some valuable information. If you were to put 0.99 here, you might be cutting off some valuable information about interpreting the table correctly. So I might have to take off something for that. This 0.99 is a little generic. But that would be the probability in this situation. I think it's pretty interesting how the first problem we start off with is one of the toughest problems. So I think this is a good problem to keep in mind, though. And so there's another part that asks us to find the probability between 1100 and 1500. So between 1100 and 1500, so this is a probability that work out fairly similarly. So between 1100 and 1500, this is the probability. 1100 less than, really equal to technically, but it doesn't matter. Remember, for normal distributions, the equal to sign doesn't matter. But remember, there's always 2 conditions. We need less than or equal to, and we need z-scores. So if anything, we can quickly go ahead and rewrite these as z-scores. The 1100, remember the 1100, I'll write this up top here. 1100 minus the mean, which we found to be 1246.775, divided by 100.49. 1100 minus 1246.775, divided by 100.49. Negative 1.46. X becomes Z because these are z-scores. We do the same thing for 1500. 1500 minus 1246.75 divided by 100.49, 2.52. But again, we can't throw this into the table because the inequalities are not of a specific format. You have to have variable is greater than or equal to number. But remember what this says. What this says, and we've done a few problems like this in the notes, when you have a compound inequality, you rely on the larger z value, or the larger z-score, and what you subtract from that, because you're ultimately subtracting, this is not an addition, is the other inequality, which states that z is greater than or equal to negative 1.46. So notice the inequalities are different because they are different in the compound inequality. One of them, z is greater than a number. The other inequality, z is less than a number. So I am still keeping the inequalities explicit. Now, one of these is already ready for us to compute, the first one. Because this is z less than or equal to number. We have both criteria satisfied, z-score and less than or equal to. So we could go ahead and plug that one in immediately. The other one is not ready because the other one, the inequality is facing the wrong way. So we have to fix that. So really, what we need to do from here we have to complement it. So technically, we lose the equal to part, but again, it doesn't really matter too much. So we have to complement the second one. And then we did this because now all of these probabilities are stuff we can bring straight to the table because now all the inequalities are facing the correct way. We have to have variable less than number. So we can bring this straight to the table. So 2.52 is one of them. And this is a positive z-score, so I'm going to use the positive z-score table. 2.52, 2.5 is down here. And then 0, 1, 2, which gives us 0.9941. So 0.9941, the first one. And then the second z-score was negative 1.46. Negative 1.46. I'm going to go to the negative z-score table. Here's negative 1.4. 6 is this column. That's 0.0721. 0.0721. Minus parentheses 1 minus 0.07. 0.0662 is our final answer. So this one problem covers, this one problem covers the whole chapter, which it's remarkable that this is the first problem that came up. Not very refreshing, but it happens when you shuffle 32 questions. The probability of this occurring is 1 out of 32. Remarkable. Okay, we're definitely going to see problems similar to this. Don't think that every problem is characterized by this, long sequence of steps, but this is a good problem to do. This problem or whatever similar problem, if you want one problem that looks at the whole chapter simultaneously. And there's problems in here that breaks up chapter 7. But does anyone have any questions before I move on? If not, let's look at the next one. All right, now we have a much easier problem. They give us they tell us it's a normal curve, and they want us to find, so one part of this problem is knowing what the symbolism means. This is the mean. This is the, technically the population standard deviation. So one part of this problem is remembering that the symbolism means the mean and standard deviation, which means you have to interpret this graph. Well, if anything, what's the mean?
4.
Yeah, it's 4. Pretty simple. Mean's always in the middle. Mean's right there. What's the standard deviation? Yeah, 2, because standard deviation is the how far the increments are. Notice it goes by 2s. So that's it. It goes by 2s. So that's a lot easier than the last problem. So this is pretty much along the lines of interpreting a normal distribution. Could you construct a curve like that given the mean and standard deviation, or can you determine the mean and standard deviation from the graph? Either one would be completely reasonable to ask on Wednesday's test. Let's move on. Okay, remember, regression stuff is on the test. The regression line and the coefficient of determination, as it's called. So basically section 4.2, I believe, from the notes, that is on the test as well. We didn't cover it on the last test. The good news is there's only 3 data points here. So to do the regression stuff, well, this is assuming you have your diagnostics turned on in the calculator, which if you don't, I do have it in the notes on how to do this. If you've done this once already and haven't reset your calculator, you don't have to do this again. But remember, for the regression stuff, well, they give us X values for the first row, 145, Y, the corresponding Y values, 3, 0, 3. You forget this process on how to do regression stuff, go check the notes. But I'll demonstrate it here as well. Right out of that, we go to stat, we go to calculate, and there's linear regression. It's the 4th one here. Linear regression already takes both lists into consideration. It's programmed to automatically take those 2 into consideration. So you don't have to type in anything else. And what they do is they give us A, B, R squared, and R. If they don't give you R squared and R, then your diagnostics are not turned on. But they give us A and they give us B. I guess while I have both of these up, this might be hard to see, but they want us to find the regression equation. Now, of course, being my math lab, they switched up A and B. A has to always be next to X, so I'm going to put A over here. This is going to be 1.38. AX plus B. So this, if you do a paper test, though, you don't have to worry about this. It's just a my math lab thing. 4.62. Again, they switched up A and B because they put the X. They didn't put it in MX plus B form. They put it in B plus MX form, which is kind of annoying. But so here's what we got for the calculator, and here's how I transcribed that to corresponding regression equation. It's the regression equation. And then after this, they want us to graph the regression equation, which I may very well ask for you to do in some regard. Again, I would give you a template, and you'd have to plot out the points and put some sort of close fit for the regression line. Now, one thing to notice here, since this is multiple choice, the calculator tells me that R is 0.96, which immediately tells me that two of these answers are immediately dead wrong. The R stands for the correlation coefficient. It tells you the slope of your regression line. R is positive. Two of these graphs do not have a positive line. B and C, their lines are going downwards. So those can't be right by virtue of the regression line. So we're not looking at either of those two. Or if you plot out each one of these points, there's only 3 of them. Shouldn't take too long. 1, -3. That's one of the points. A is already wrong because for 1, it goes up and not down. A's up. It has to be D. That makes sense because the point here is 1, -3, which is what the rest of the graphs fail to do. So that's it for this problem. So that's how to find the regression equation in the calculator. And the regression line, normally the way to graph a regression line is by, well, the leftmost part of the graph is normally the y-intercept. And then the rightmost part of the graph, I might just tell you what it is. I might just say, draw the regression line by finding the y-intercept, finding the value for when x is equal to 10, or whatever the furthest value on the right is, and then just draw a line connecting them. I would just tell you that. Make it a little bit easier on you. You don't have to derive it yourself. But that would be a very fair question to ask. Does anyone have any questions before we look at the next one? Okay, let's keep going. Did I miss? Oh, okay. Okay, so like we had on the previous test, there were, when you started off the test, there were problems that looked at, is this variable continuous or discrete? Is this variable this or that? There's not too many binomial outcome problems, yes or no problems, in this section of that caliber. So instead, you can expect the first few questions on the test, just like the last test, to be some straightforward definition problems. So any of the definitions, or maybe any of the simple formulas. I might just ask you, which one's the expected value for a binomial distribution? Or yeah, a binomial distribution. And you would say it's just n times p. Stuff like that, or any definition here. And I put a decent a subset of definition-based problems that I can easily pull from. There's quite a variety, so you can do this practice test a bunch of times and you'll probably see a bunch of different examples. So here, this is just a conceptual understanding of what the least squares regression line represents. And so this is where you have to understand that this is referring to, really, it's predicted y values. Remember, the regression line gives you an idea about predictions, not about actual values. It's based off of actual values, but we use regression to predict things, to either interpolate various values or extrapolate values that may not immediately be in the scope of our problem. This is used a lot with the stock market. They will make regression models because you don't know what's going to happen tomorrow with the stock price, but you can try to get some fundamental idea by building some model, and it might tell you, or extrapolate that information to tell you what they might think the stock price is tomorrow. So it's about predictions. Okay, so in this problem here, they do say least squares regression. So at least it gives us an idea of what section. This is what I always do when I start a problem. I try to figure out what section or chapter does this put me in. I see the word regression, I immediately think chapter 4. So at least it narrows down your thought process. So no normal distributions, no probability stuff, nothing like that. And they also gave us the regression line. Remember, the regression line is always y with the little hat on top. And they say this model applies for a very particular domain of x values. And the first question is, they want us to interpret this. And in particular, they want us to first interpret the slope. Now, the slope, notice they have a little template here for us. For every unit increase in blank, the, well, other variable falls by blank. Okay, that seems fairly vague. So the slope here, if anything, so hopefully you remember it enough high school algebra to know that the slope is always next to the x. It's negative 0.0487. Now the slope, one way you can think about it is rise over run, or another way you could think about it is loosely y over x. Now this is kind of a loose interpretation because technically it's y delta and x delta. I won't nitpick on that too much. There's a few different ways you can interpret this. But the only reason I'm writing it in this manner is because y, well, y and x tell us an idea about the way in which the slope can be broken down. Because any number can be written over 1. So for every unit increase in x, which means we need to figure out what x is. And it seems like they say that x is the literacy rate, x. So for every unit increase in the literacy rate, the y value, which is the I guess the other one, the age difference, falls by blank units. Now, that's where the slope comes into play. But you already used the word falls, so they took care of the negative sign right there. I'm going to put the positive value. See, if I gave you $10, I'm not giving you negative $10, even though I lose $10. By giving you the money, it's understood that I am losing that money based off of the context. Mainly use negatives for computational purposes, just like with percent and proportion. So that's one way to explain this way in which we break down the slope. Now, they also ask about the y-intercept. Now, I explained this in class that the y-intercept is always found when x is equal to 0. That is pretty much the way in which you find the x-intercept, or the y-intercept, rather. And they're asking, does it make sense to look at this problem for x is equal to 0? Now, they do say the model is applied for when x is in between 23 and 100. Now, what's interesting about this problem, it's normally a lot more straightforward than other problems. Actually, never mind. All right, so x is the literacy rate. So this is saying x equals 0 implies that someone has a literacy rate of 0. And based off of our model, we could say that this seems, well, is it impossible? Is it outside of the scope? Now, if anything, we definitely know that it's x is equal to 0. So x value of 0, x value of 0 can't be either of these two because they say y value. We're not looking at y values. And of course, we already figured out that it's not the top one. Well, imagine, is it outside the scope, or is it impossible to have a literacy rate of 0? I feel like this is my math lab kind of nitpick thing. I would not think of anything to closely resemble this if I were to ask a question like this. So I don't know, that sounds kind of relative. Is it possible to have a literacy rate of 0? I mean, there would have to be some extreme circumstance, but let's just say it's impossible. I don't know. Again, this sounds too ambiguous. Maybe it is the other one. I don't know. Is it outside of the scope? Maybe. They seem a little bit synonymous to me. But in any case, the more important thing here is to identify what the y-intercept represents. And it means when x is 0. And if I were to ask this on a test, I would say, why do you think, or would you trust this or not? Why would you not trust this? Or, why would you not look at the y-intercept? And you would just kind of explain it in whatever layman terms you want. I'll probably accept anything that sounds reasonably close to anything remotely cognitive. So they also ask for us to make some predictions. Predict the age difference between a husband and wife in a country where the literacy rate is 45%. Well, whenever we predict things, remember, we have a regression model to help us predict things. In fact, I'll just rewrite it. Now, they tell us the literacy rate is 45%. And above, we see that the literacy rate is x. Well, plug in, what this tells us is that x is equal to 45. And they do confirm that by saying we're using the percentage and not a proportion. So we are using 45 directly. So really, you're just plugging 45 into the regression model. again, this is one of the helpful reasons of having a regression model. 45 may have never been an explicitly collected data value. This would be more so of an idea of interpolation. We figure out an in-between value given some surrounding values. So just plug this into the calculator.
And you would compute it by like the decimal of 45%, right? You would just leave it as 45.
We leave it as 45 because they do say here, when they mention the literacy rate, they want it as a percent. So that's a contextual thing. Negative 0.0487 times 45 plus 6.8. So this says if the literacy rate is 45, then you can expect this age difference, as it's referring to be 4.6085. They'll probably ask for some decimal places, around a 1 decimal place. So really, that's 4.6. Now, would it make sense to use this model to predict the age difference where the literacy rate is 17%? Now, they do tell us, again, the literacy rate is referring to the X value. And it does say that we use this model anywhere from 23 to 100. So of course, we're not using 17. So it's not a Y value of 17, anything, it's an X value of 17. And it's outside the scope of the model. It says this only trust this model for 23 to 100. There's another problem here on the exam that it has something to do with how long students sleep and how well their test grade is, and they have a regression line for it. And then it says, well, if you try to extrapolate this model, it would imply that if a student slept for 15 hours, then he's going to make 130% on the test, because of course the linear function just increases without bound. But that doesn't make sense. There's a limit. There's a ceiling, of course. So that's another way to think about how extrapolation doesn't always work with linear regression models. Just in the real world, if you were a statistician looking at this stuff, domains are important. Okay, so here, would have been really cool to have my statistician friend over at Facebook to come by and give a little chat with you all about what he does. He makes a lot of money. Statisticians make a lot of money. Okay, so literacy rate in a country is 99%, which is in our domain of values. So just something to keep in mind. And the age difference is 1 year. So they gave us an X value of 99, and they also give us the Y value of 1. Is this above or below the average age? So basically they want us to compare the observed value. The observed value is 99,1. The expected, or predicted rather, expected is not the right word, predicted is whenever you have 99 for X, what does our model give us, or the predicted value? So they say 99% literacy rate. So it's the same thing as before here, just 99. Oops, it's 95. 9. 1.9787. So they're wondering, how does the observed correspond to the predicted? So in other words, how does the observed y value of 1 compare to the predicted y value of 1 point, or roughly 2 here? So they want to know, is the observed above or below the predicted? And it seems like it's below. And it says the average age. So basically it's asking us to compare this to the predicted value we just found, which was 1.977. It does say the average age because this is found from a predicted model, which gives us this average or expected understanding of values. I mean, of course, it's not going to be perfect. Our goal, the goal of a statistician is to be as close to the real values as possible with their models. So this is a pretty good regression problem, more so on the interpretive aspect. Didn't really do much in the calculator. Does anyone have any questions before we move on? If not, let's go ahead and look at 6. Okay, so this is talking about, so this may look familiar. Remember, we started talking about discrete random variables. And in this case, this is going to be very similar to when we talked about discrete versus continuous variables, just in general. Here it's the same type of problem, just they use the word random variable now. But it's still the same idea. The number of hits to a website in a day, would that be considered discrete or continuous?
Right.
Yeah, it'd be discrete, definitely discrete, because the number of hits to a website, well, you can have nobody show up or one person show up, 2 people, 3 people, 4 people, never really anything fractional. So that would tell you discrete. So it's discrete, and we're going to go with A because that one actually splits up. Instead of D, which just says any value greater than 0, which could be 0.5 or 1.75, 2.667, we're going to go with the top. And then the next one is the weight of some steak. Yeah, well, by the 50-50 hope, this one's continuous. Weight in general is something that's continuous. This would be a continuous one, and we're going to go with D, where notice that they do not have an equal to part because a weightless steak would be rather interesting. But so this is a continuous value with an inequality to represent values that may be decimals. So that should be a pretty straightforward problem. Let's look at another. Okay. They're asking, all right, so this is kind of definition based. Is this a probability model? This means you need to know what a probability model is. Probability model has 2 conditions. The probabilities have to add up to be, well, 1, and none of the probabilities can exceed 1 or be less than 0. So obviously, we can look at this and tell that none of the values are less than 0 or exceed 1. So that part is checked. Sounds like you were furiously typing over there. So what did you get from your 1.05? So if you add up all of these, because that was the second condition, you add up all of these, you have to get 1. If you don't, it's not a probability model. So 25, 50, 75, 85, 95, and then 1.05. So because this is not equal to 1, that's not good. So I'm going to pick the last part for, is this an example of a probability model? Definitely not, because the probabilities don't add to be 1. Simple as that. Now, what do we call the event yellow? So we could still interpret the probabilities nonetheless. So they're asking about what yellow would be considered from a definition base. Well, yellow has a probability of 0. So this would be an impossible event. Something with a probability of 0 has no chance of occurring. So that would be impossible. Remember, an unusual event in general, unusual events are characterized by having a probability of less than 0.05, less than 5%. It's an unusual event, less than 5% chance of occurring. Okay, so this part, it talks about the standard normal curve. So that gives us an idea of which chapter to consider. So standard normal curves, well, since it's standard normal, we don't have to convert anything from values to z-scores. They give us the z-scores. To the left of some z-score or to the right of another z-score. Well, they first want us to choose the correct graph. Obviously, this one does not show to the left of -1, so that one can't be right. This one has to the left of -1, but it doesn't have to the right of +1. That one's not very good. This one is completely antithetical to what we're asking for. Let's see. There we go. To the left of -1, good, or to the right of +1, good. So the last one seems like the correct shading. You need to see that again. And it's shading the tails. But anything involving, well, they tell us the total area under the curve for these corresponding z-scores. So this is when we use the table in the back. Now, what they're doing is you're telling us here this area for the left of z is equal to -1. So this is when capital Z is less than -1. To the right of z is equal to 1. So this is when z is greater than 1. So this is not a compound inequality. These are two separate inequalities that we're just adding together at the end. Well, the good news is one of these is already ready for the table. We already have the z-score, so we don't have to convert anything. So we can figure out that z-score immediately. The other one, we have to do a little bit of work because the inequality is not facing the right way. So really, we have to complement it. So 1 minus, or rather, so yeah, 1 minus, I guess we could put the probability notation. Z is less than or equal to 1. So we can figure out both of these separately. I'll just put them both down here. Again, the equal to sign does not matter in normal distributions. But we can find both of these individually. The inequalities are now facing the right way. So let's find the z-score, or the area, which corresponds to the probability for -1 and for +1. Go ahead and start off with -1. And I'll use the standard normal table that has the negative z-scores because we have a z-score of -1. And it's -1.00, so it's the very first one. It's 0.1587. 0.1587. And then for the other one, we have a z-score of +1. +1, we'll scroll down a little bit. Positive 1 seems to be right here. And because there's no tenths or hundredths place, particularly no hundredths place, it's in the first column, 0.8413. But remember, it's 1 minus this value because we had to complement the inequality symbol. And so that one we can figure out right fast. 1 minus 0.8413. 0.1587. So naturally, we can expect symmetry here because -1 and +1 are the same distance away from the mean. You do recognize this, it'll save you a bit of work. But in any case, we have to add those two together. I'll just put this over here again so we can emphasize the addition that follows. So we have to add both of those two together. And this is 0.3174. And that's our answer. Because the 0.1587 is to the left of -1, and to the right of +1 is also 0.1587. It's just a coincidence. Or in general, left and right areas are not going to be the same, but it is in this case because the z-scores have the same magnitude. And this is utilizing the symmetry of a standard normal curve. So the next problem, you will not get the same probabilities because the z-scores have different magnitudes. Okay, so let's look at the next one. So the next one is -1.37, 2.37. And so this, it's the same idea. Start off by figuring out what's a shade. This one's looking pretty good so far. I'm trusting it's going to be D. That one's not right. This one is the antithesis of what we're looking for. And C is not correct either. So it's D because to the left of one z-score or to the right of the other means we're shading the tails. So you see here we're shading the tails, a little bit to the left of -1, cool. A little bit to the right of 2, looks good. This would be the correct region. And now they ask for the total area. So it's pretty much the same problem as before. To the left of this or to the right of this. So to the left means we have a less than sign, -1.37, so we'd have to figure out its corresponding area. This one's to the right, so this is a greater than sign, 2.37, which means we would have to complement that one. And then we add the two areas together at the end. For the second one, just like we did before, we will have to complement it so we can have the correct inequality. Technically, we get a less than or equal to. Again, the equal to doesn't matter with normal distributions. So we figure out these two, we add them together at the end. So -1.37. Here's -1.3. And then 7 seems to be right here. So we seem to get 0.0853. 0.0853. .0853. And then the other one, we have a z-score of 2.37. We go to the positive ones. .37. Scroll down a little bit. 2.3 is right here. And then 7 would be here. 0.9911. So really this is 1 minus 0.9911. And we can figure that out right fast. Zero, 0.89. Add these two together and get 0.0853. 0.0942. That would be the answer. So 0.0942. Does anyone have any questions about this? I'm not going to do the last one because it's the same problem. See if we can fit one more problem in. Okay, so they found some, so first number we have 67%, and there's 450 people in general. Compute the mean and the standard deviation. Now, you might look at this problem and think, well, where's the data set? How do you find the mean? How do you find the standard deviation? There's no data set. Well, you have to acknowledge that this is a binomial probability distribution. Remember, binomial probability distribution is when the outcomes are true or false, yes or no, success or failure. So moral values is poor. That's it's either poor or not poor. So that would be binomial. And so the mean is always n times p. That's just a formula you have to know. And there's no calculator that's really going to, you don't need the calculator unless you're just computing this. And there's 450 people in total. 67% is 0.67. This will give us the expected value. And naturally, they want us to round to the nearest whole number because this is referring to adults. So 302 for the mean. And then the standard deviation, I believe that's the square root of NP times 1 minus P. Is that correct? Okay. So we already know N and P. N is 450. P is 0.67. Or 50 times 0.67, 1 minus 0.67. And that's just something we throw in the calculator. As such. 50 times 0.67, parentheses, 1 minus 0.67, close, close. 9.97 roughly is the standard deviation. They went to the nearest tenth. So the nearest tenth would actually round this up to 10. The 7 would bump the 9 up to, well, 0 and carry the 1. So that'd be 10. And then for every, since I'm out of time, the mean is the number that would be expected to believe that this is poor, because the mean is the expected value. It's not really the minimum. It's not really giving you a range. It's just giving you an expected value. All right, I'm out of time. Test is Wednesday. Quiz is due tonight, so make sure you do the quiz. And I recommend at least looking at one practice test. There's a good variety of problems. Other than that, sign the roll sheet if you didn't do so already, and have a good day.